Here's the simplest test in all of calculus, and you already know it in your hands. Can you draw this graph without ever lifting your pen off the paper? Watch. The pen starts on the left and glides all the way across. Up, over, down. One single, unbroken stroke, never leaving the page. That is a continuous function. No breaks, no holes, no jumps. Now this one. The pen runs along the lower level, reaches the middle, and the graph suddenly leaps upward. To carry on, you have to lift the pen, hop up, and set it down again. That lift is a break in the graph, a discontinuity. This whole lesson is about pinning down. Exactly what it means to have no break at a point, how breaks can go wrong, and why smooth functions matter so much. Let's make it precise. We say a function is continuous at a single point. X equals a when three things all hold at once. Miss any one, and the graph breaks there. Condition 1. The function actually has a value at a. If f of a is undefined, a gap where nothing is plotted, you fail before you start. Condition 2. The limit as x approaches a exists. A single finite value the curve heads toward from both sides. This is exactly the limit you already know. A jump kills it, because the two sides disagree. And condition 3, the one that ties it together. That limit must actually equal f of a. Where the curve is heading and where it truly lands must be the very same point. In fact, condition 3 quietly contains the other two. So the whole definition of continuity at a point compresses into one clean line. The limit of f as x approaches a equals f of a. When continuity fails, it fails in one of a few classic ways. Let's meet the whole family, one clean picture at a time. First, the gentlest break, a removable discontinuity, a single missing point punched out of a smooth curve. The limit exists, the pen is clearly heading for that spot, but the point itself is either absent or misplaced. One open circle, a tiny hole. It's called removable because you could fix it by redefining that one point. Just drop the dot into the hole, and the curve is whole. Again. Second, the jump. The left side settles at one height, the right side at a different height, and the two simply refuse to meet. Left hand limit 1, right hand limit 3. Here the second condition fails. The limit doesn't exist because the sides disagree, and no single value you place at a can bridge a genuine step, so a jump is not removable. Third, the infinite discontinuity. Near the break, the function doesn't settle at all. It blows up, racing off toward infinity along a vertical wall. 1 over x is the classic. Dive to minus infinity on the left, soar to plus infinity on the right. And the strangest of all, the oscillating break. Sine of 1 over x. As x creeps towards 0, 1 over x explodes. So the sine swings up and down faster and faster, infinitely often. It never settles on any value, so no limit exists. Let's work one all the way through. Take x squared minus 1 over x minus 1 everywhere except at x equals 1. And at that one point, we are free to set the value to some number k. The question, which k makes f continuous away from 1? Factor the top. X squared minus 1 is x minus 1 times x plus 1, and that x minus 1 cancels, leaving simply x plus 1. So the limit as x approaches 1 is just 1 plus 1, 2. The curve is a straight line heading dead end for the height 2. Now the rule, for continuity, the value we place must equal the limit. The curve is aiming at 2, so we must set f of 1 equal to 2. That is, k equals 2. Watch the graph heal. Drop the point right into the hole, and the line is whole. One continuous stroke. Any other value of k would leave the point floating off the line, and the break would stay. A second, more useful kind, a piecewise function, 2x plus 1 below 3 and kx minus 5 from 3 onward. The only place it could possibly break is the seam at x equals 3, where the formula switches. Find k that makes it continuous there. Condition 1. F of 3 is defined. The piece with the equal sign, x greater than or equal to 3, applies here. So f of 3 is 3k minus 5, defined for every k. Condition 2. The limit must exist, so the two sides must agree. From the left, use 2x plus 1, 2 times 3 plus 1 is 7. From the right, use kx minus 5, that's 3k minus 5. Set them equal. 7 equals 3k minus 5. Add 5. 12 equals 3k. Divide by 3, k equals 4. That's the value that makes both sides meet. Condition 3 checks itself. With k4, f of 3 is 3 times 4 minus 5, which is 7. Exactly the common limit. All three conditions hold. And look at the graph. The two line segments now meet perfectly at 3, 7. No jump, no hole. One continuous join. Here's the good news that saves enormous effort. Continuity is contagious. Combine continuous functions in almost any ordinary way, and the result is continuous too. Add to continuous functions. Still continuous. Multiply them. Still continuous. Divide them, and it's continuous everywhere, except where the bottom hits 0, the one place a quotient can break, and feed one continuous function into another. The composition stays continuous. So sums, products, quotients, and compositions all preserve it. To headline consequences, you'll lean on constantly. Every polynomial, like x squared plus 3x minus 5, is built from adding and multiplying, so it's continuous absolutely everywhere. No breaks ever. And every rational function, one polynomial over another, is continuous everywhere, except the handful of points where its denominator is 0. So for x squared plus 1 over x minus 2, the only trouble spot is x equals 2. Everywhere else, perfectly smooth. Continuity buys you one genuinely beautiful guarantee, and it's pure common sense once you see it. If you draw an unbroken curve from a low point to a high point, it has to pass through every height in between. It simply cannot skip a level without lifting the pen. Here's a continuous curve, running from the point A, f of A on the left, up to B, f of B on the right. Pick any height and strictly between the low value and the high value. Slide a horizontal line across at that height. Because the curve has no gaps, it is forced to cut clean through that line, at least once. There's the crossing point C. That's the intermediate value theorem. A continuous function on a closed interval takes every value between f of A and f of B at least once. And here's why that matters. It proves roots exist without ever solving for them. Take h of x equals x cubed plus x minus 1, a polynomial, so it's continuous. Check its endpoints. At 0, h is minus 1, below the axis. At 1, h is plus 1, above it. The function is negative at one end, positive at the other. 0 sits between minus 1 and plus 1. So by the theorem, the continuous curve must cross the axis somewhere between 0 and 1, meaning h has a root there. We've proven the equation has a solution without finding it. It happens to be near 0.68. Your turn? Here's a piecewise function, x squared below 2 and a times x from 2 onward. Find the value of a that makes it continuous at x equals 2. Match the two sides at the seam. Pause the video, work it out, then come back. Here's the walkthrough. From the left, x squared approaches 2 squared, which is 4. From the right, ax approaches to a. Set them equal for the limit to exist. 4 equals to a, so a equals 2, and the check confirms it. F of 2 is 2 times 2, 4, matching the limit. Continuous. If you found a equals 2, you've mastered the core move. Trap 1. Thinking the limit is the whole story. The limit can exist and still miss f of a. All three conditions matter. The value must actually equal the limit, not merely approach it. Trap 2. Confusing removable with non-removable. A hole is removable. Redefine one point and it's fixed. But a jump, where the two sides differ, can never be patched by any single value. Trap 3. Treating an infinite blowup as fine. If the function races off to infinity near a, the limit does not exist as a finite number. The function is discontinuous there. Full stop. And trap 4. Continuity at a single point is not the same as continuity on a whole interval. A function can be smooth at one spot, yet broken right next door. So always say where. Let's lock it in. A function is continuous at a when the limit there equals the function's value. What it's heading for is exactly where it lands. No lifting the pen. When that fails, it's one of four breaks. A hole, a jump, a blow up to infinity, or an endless oscillation. Only the hole is removable. Most functions you meet come continuous for free. Every polynomial everywhere, and every rational function except where its denominator vanishes. And the payoff, the intermediate value theorem. A continuous curve hits every value between its ends, which quietly guarantees that equations have solutions. Hold these, and continuity is yours.